Hi, this talk's called Reasoning About Uncertainty in Empirical Results, and it's by myself, Neil Walkinshaw, and Martin Shepherd. Um, so, the motivation for this talk. Experimentation is essentially an exercise in managing uncertainty. Experiments can have all sorts of sources of uncertainty. You see some on the right there. There might be a lack of data, intrinsic randomness, your choice of participants for the study, etc. Various ways in which the validity of your outcomes can be threatened. And over the years, there have been many meta-analysis techniques that have arisen to reason about experiments and to factor in these sources of uncertainty. You've got narrative synthesis, aggregated data, individual participant data, etc. And within all of these approaches, there is, however, one commonality, and that is that the uncertainty about the findings or the outcomes is implied by the statistics. You might have a low effect size or a high confidence interval, for example. Now, one of the problems that we're trying to address is that uncertainty can be difficult to interpret. On the one hand, you might ask, well, is this intrinsic to whatever phenomenon that we're studying, this uncertainty? Or is the uncertainty in the results due to, for example, a lack of data, an unsound methodology, or some problem in the way that we've set up the experiment? So that's the motivation for this paper. The way we propose sort of trying to work around this is to adopt a framework that allows us to explicitly reason about uncertainty and to make that distinction that we just mentioned in the previous slide explicit. So for that, we propose the use of subjective logic. In the words of its developer, Odun Josang, it's a formalism for reasoning under uncertainty. It's a generalization of a long-standing reasoning approach called Dempster-Shafer theory that dates back to the 70s. So subjective logic is based on this notion that the thing that you're reasoning about, or the things that you're reasoning about, are captured in what is known as subjective opinions. So a subjective opinion, in the sense that we're using them in this work, is basically a statement of some true or false statement. Okay, these are known as binomial subjective opinions. For example, test-driven design is better than iterative test last. To take one example from a study on meta-analyses. So basically, in order to capture a subjective opinion, you capture it in these three dimensions. You have belief, disbelief, and uncertainty. And for each one of these, you give it a value between 0 and 1, under the sort of constraint that all of them have to add up to 1. So once you have a subjective opinion, it can be visualized as this triangle here. This is known as a barycentric triangle, where you have one axis for uncertainty, one axis for disbelief, and one axis for belief. So, for example, if you dogmatically know that something is true, it would be 1 for belief and 0 for disbelief and 0 for uncertainty. Conversely, if you know that it's false, you'd have a 1 for disbelief, and so on. It also has this interesting third opinion, which is the ability to be completely uncertain about something. If you've looked at all the data and the data you decide doesn't help you at all and doesn't give you anything of any information that you can use to corroborate the hypothesis you're working on or otherwise, you can have a completely vacuous opinion. Uncertainty is 1, and disbelief and belief are 0. Another nice property is that if you do have a subjective opinion in the form of this barycentric triangle, you can translate it directly into a beta distribution. So, for example, here, if you have a subjective opinion with a high level of uncertainty, that translates to quite a flat beta distribution. And you can get these automatically, and you'll see more of these as we go through the talk. So that's how to represent subjective opinions, and of course, because we're dealing with a logic, there's also operators by which you can sort of operate upon these opinions, and there's a lot of them. We're not going to go through all of them, but the nice thing about them is that when you're combining these opinions together and you're reasoning about them, the uncertainty that's ingrained within them stays a sort of first-class citizen. It's one of the primary elements that stays throughout the reasoning process. Subjective logic comes with a lot of what are known as fusion operators, so ways to combine subjective opinions to produce an aggregated opinion. And that makes them, we would argue, especially useful for things like meta-analysis. So we're going to use, there's lots of fusion operators out there, and you can look up the literature on them, but there's one called multi-source weighted belief fusion by van der Heyden, and that's really useful. That's what we're using here, because you can combine more than two opinions, and it lets you, it weights different opinions according to their levels of uncertainty, which makes it useful to aggregate results that have different levels of uncertainty associated with them. So you might get sort of three diverse opinions here, and then the fusion would be taking these all together, and this would be the sort of fused opinion according to van der Heyden's fusion operator. And the maths for this are in the paper. You can look at van der Heyden's paper for that. So that's basically our idea, is to use subjective logic to fuse together different experimental results. So the idea is that you might have your various experiments. They might be very heterogeneous. They might be almost exact replications of each other. It doesn't really matter. The whole idea is that once you have experiments and the experimental data or the summary data of these experiments, you use these to produce for each experiment subjective opinions, and then because we are able to operate on these subjective opinions, we can do things like fuse them all together to get an aggregate opinion, which gives us a nice, transparent, justifiable sort of aggregate opinion for the experiments. So in order to try this out and to see how it works, we decided to apply this to a case study, and the kind of case study we chose was a meta-analysis of this sort of long-standing question in the community of programming languages versus defects. Now, there's been quite a few studies on this, and we picked out two. The first study we picked was by Ray et al., a large-scale study of programming languages and code quality in GitHub. It was published at FSE in 2014, and what they did was they picked 728 GitHub projects developed in 17 different programming languages. They identified faults by analyzing commit messages in the version repositories. So if a commit message had something like bug fix, or it had a hashtag and then what looked like a bug ID number, they would say, right, that whatever that code is a bug fix, and they basically used this to count up the number of bug fixes per language, and they fitted that to a regression model, and they used the coefficients of the regression model to indicate how defect-prone different languages were. And then, so that's one of the studies, and then we also looked at another one that is actually a very different study by nature, but that is looking at very similar questions. And this was published at ICSI in 2015. It was by Nance and Furia, and it's called A Comparative Study of Programming Languages in Rosetta Code. So what they did was, so Rosetta Code is basically a repository of solutions to relatively simple programming problems written in lots of different languages. So they took 745 of these tasks across the 8 languages. And they basically, again, they identified the fault proneness, but instead of looking at commit messages like in the previous study, they looked at the failure rates by running the programs that were written in that language and by seeing whether they failed or whether they hit a timeout. Now, one of the questions that Nance and Furia asked in their paper, and that we're basically using as the guide for our meta-analysis, was this. Are strongly typed languages, such as Java or C#, more or less defect-prone than weakly typed languages, such as Ruby or Python? So we thought that would be a really useful question to ask in our meta-analysis, and for this we're going to use not only Nance and Furia's data, but we're also going to use the data from Ray et al., or the summary data from Ray et al. So you can see that there's a sort of challenge there from a meta-analysis standpoint. There are different types of data. You've got GitHub commits versus recorded failures. The Nance and Furia study uses 8 languages. The Ray et al. Study uses 17 languages, although 7 languages feature in both. And you've got different methodologies at play. There's different threats to validity. For example, in the data for Ray et al., we're not actually using their raw data. We're just using the published the published coefficients and the sort of data that was available in the paper. We didn't, for example, from that we weren't able to discern what the power was, the statistical power that's associated with each coefficient. For the Nance et al. Study, you could ask the question whether counting timeouts is a valid way of equating that to a failure, because it might just be that the program's running slowly. It might not actually equate to a defect. For the Ray et al. Study, you've also got the sort of long-standing question of whether using commit messages is a valid basis for actually homing in on defects and so on. So all sorts of different sources of uncertainty, which makes them sort of interesting for us. So basically what we did was we encoded the experimental outcomes as subjective opinions, where you calculate a level of uncertainty based on these various factors that we described earlier. Then you calculate a level of belief based on the effect size or the coefficient, depending on what study you're looking at. And then because you've got the uncertainty and the belief, you can scale them down and you get the disbelief, and then you get your sort of coordinates. And broadly speaking, you've got this sort of disbelief to belief on that axis and uncertainty on that axis. So then if you look at the Nance and Furia data, we basically took, we grouped the languages into weakly typed languages and strongly typed languages. We computed the subjective opinion for each of these, and you see them there, and you see the beta distributions for them as well. And because you can then fuse these together in terms of their groups, you end up with a fused opinion for weakly typed languages and a fused opinion for strongly typed languages. And here you can see that for weak languages, there's a sort of stronger effect size. So they're more, weakly typed languages tend to lead to more defects than strongly typed languages in the Nance and Furia data. And that's essentially what they also found in their paper. And then we did the same for the study by Ray et al. They had more languages, but we similarly grouped them. And again, you end up with a fused weak opinion and a fused strong opinion. And what we see here again is that the weak languages tend to ever so slightly lead to more defects than the strongly typed languages. And then, because this is a meta-analysis, what you can then do is fuse them together. So you can take your weak fused versions. So this is the weak languages from the Ray study. This is the weak languages from the Nance study. You see there's a strong difference in uncertainty there. And here's the strong languages, the strong fused opinion from the Ray study, and the strongly typed languages from the Nance study. And again, you can fuse them together, and what we end up with is this sort of overarching meta-analysis. So from both studies, if we fuse together the subjective opinions from the weakly typed languages, we get this opinion here, and for the strongly typed languages, we get this opinion here. And indeed, we see that from both studies, weakly typed languages tend to lead to more defects than strongly typed languages. And that does actually tie in with what they found on their studies as well. So that brings us to the conclusions and future work. So what we've found is that subjective logic does enable us to quite transparently reason about and combine empirical data or results from empirical data. And the nice thing about this is that uncertainty is a primary component. It lets you very much discern between what is actually uncertainty and the relationship between that and the belief or disbelief in what you're investigating. We've shown a little proof of concept about how this can apply to meta-analysis, spanning different types of data. But there is a lot of work yet to be done. Okay, so what we I think we'll admit is that we were relatively ad hoc in terms of encoding the subjective opinion and figuring out how to encode the uncertainty, and we need to do a bit more in terms of sort of developing a more structured methodology by which to encode these subjective opinions. There's lots of different operators and fusion operators that would be good to look at as well. And there's a whole world of other types of opinions out there. So, for example, it's very straightforward to extend all of this to, for example, reason about multinomial opinions, where you have opinions that can represent not just true or false, but lots of different alternatives as well. And that's where we'll be going in the future. So thank you very much.